Okay. So I was thinking about going over our exam today, but instead of doing that, instead of taking up class time to do that, if there is a request for it, if you guys want to see, if you want an exam one review, I'll just record that outside of class and then just upload it to Canvas. Basically, like me working through the exam one. Now you can see, you should be able to see the solutions to the problems in WebAssign as well. Okay, so I'm going to jump straight into the next chunk of material, which is going to be chapter 2. So we're moving into chapter 2 now, which is just called functions. All right, so in section 2.1, we're going to, in 2.1, which is also just called functions, we're going to be talking about what is a function, so the definition of a function. I'll give you the formal definition of what a function is, but since the formal definition is a little strange, you may not have seen something like it before. We'll do a lot of examples with it to make sure we're all on the same page about what a function is. We're going to talk about domains and ranges of functions. More so on the domain side, but we'll talk about ranges as well. You can't really talk about domain without at least mentioning ranges. So we'll talk about what those are. And these are going to be more like definitions and ideas and concepts. But then we're going to get into evaluating functions, which is the actual like mechanics, like the actual math, like we'll be writing down and actually evaluating things. And then we'll talk about, what else are we going to talk about? Different ways to represent functions. Representations of functions. Representations of functions, meaning, well, we can represent them algebraically, which is going to be probably the way that it's going to be the most useful way. We can also represent them verbally, which is that's just going to be an exercise in making sure you understand order of operations. That'll make sense when we talk about it. We can represent them numerically, which means table of values, and then kind of culminating in the best representation besides algebraic, which is graphical. So we'll talk about verbal representations, numeric, algebraic, and graphical representations. So saying what the function does, making a table of values for some explicit inputs and outputs of the function, writing down the algebraic form of the function, which is going to be like the main way we deal with functions, and then also graphical, going from these ideas to a graphical representation. That's kind of going to be the culmination of like the first half of this chapter is going to be getting to where I can give you a function algebraically and then you can create a graph. That's kind of going to be the goal, at least one of the major goals of this chapter. All right. So that's just a little rundown of 2.1. So let's go ahead and get into it. What is a function? Okay, so that first idea, what is a function? All right, so we'll start with just kind of the basic idea and we'll try to work up to more technicality. A function is now here comes a vague term or a pair of terms, mathematical object It's just, I mean, you could literally just say a math thing. Like, this is just fancy way of saying it's just a thing. I'm being super vague here. A mathematical object that takes in values, which I'll call inputs. I like to say inputs and outputs. That's the way I like to describe them. So it takes in values, which I'll call inputs, and gives out new values, which I'll call outputs. Okay. So a function is just this math thing that it doesn't do anything until you give it values. So you give it inputs and it gives out outputs, new values, outputs. So we're going to, let's see. Let's see, what, before I get into the how we're going to denote functions, let me say we need a function. What do we need it to do? To assign exactly one output to a given input. Okay, so what do I mean by this? Like, for instance, if you input into your calculator 2 plus 2, it should just give you 4, right? It should just give you 4. If it gives you two different answers, then it's not a good function, right? So as an example of this idea, because this is going to be the major definition of a function, that it assigns one output to a given input. As an example, consider a calculator. Yeah, just consider a calculator. If you give it input, so if the input is 2 plus 2, the calculator should yield, or I'll say give 4, right? Should give 4 for some input, which is a pair of numbers here. That's fine. It's just some input. It should give a single output. Like if you plugged in 2 plus 2 into your calculator and today it gives you 4, and then you do 2 plus 2 tomorrow and it gives you 7, then that's not a good machine, right? It's not a good function. So you need it to take in an input and give out only one output. So a calculator that gives two different answers from the same input like if it gives 2 plus 2, oh shoot, if it gives 2 plus 2 to 4, and then it also gives 2 plus 2 is 7, then it is not a good function. It's not a function at all. It breaks the definition of a function. Okay. Now, I want to make a note about something that comes up here that often confuses students. A function is allowed to give a repeated output from two different inputs. And if I keep going with the calculator example, then I can say, like, for instance, if 2 plus 2 gives me 4, okay? And then I say 1 plus 3, that's a different input, but it's giving me the same output. That's okay. This is still a function. This is a good function. This is a function. Or at least it fits the definition of a function. That you're giving it two different inputs, right? 2 plus 2 or 1 plus 3, they're yielding the same output. That's okay. You just can't have two different, sorry, let me say it carefully. You can't have two of the same inputs going to different outputs. So there's a little picture here that might kind of might help out. I'll say here is a little picture of a function, something that's okay for a function to do. No. Let me keep the colors straight here, because otherwise you might get confused. Red, I'm doing red is not a function. I mean, you're probably not color coordinating your notes, but just for your sanity here, I'll keep the red font as being the example that's not a function, and then blue as being something that is a function. So a function, it's okay to have two different inputs, like input 1. So these are inputs, just denoting with little dots, inputs 1 and 2 going to the same output. So this is like 2 plus 2 gives 4, or 1 plus 3 gives 4, or 0 plus 4 gives 4. It's okay to have different inputs going to same output. So different inputs, oops, I spelled different wrong, different inputs going to same output is okay. All right. Now over here, not a function would be kind of the opposite picture. One single input. So if I like invert this picture, right? One single input for multiple outputs. This would be like if 2 plus 2 yielded 4 and 2 plus 2 yielded 7. Same input yielding or giving, instead of yielding, you can say giving. Or you can just say going to, yielding different outputs is not okay, is not a function. So not okay, I mean like not fitting the definition of a function. Okay. So what have we got so far? And I'm making a big deal out of this because, well, function definition is a big deal. Even though we won't really put it to good use again outside of this section, we won't really come back explicitly to the definition of a function and talk about it again until we talk about inverse functions. But it's still a good thing to know. Functions are like one of the most useful objects in math, especially for applied problems, applied math. You just can't do anything without functions. So that's why I'm making such a big deal out of what they are. So what have we got so far? We've got like a verbal description, kind of layman's terms idea of what a function is. We need a function to assign exactly one output to a given input. Then a little calculator example of something that would be not a good function, not a function at all. An example of something that is allowed in a function, and then a little picture that kind of puts that all together. Okay. Now let's talk about this official definition. But first, in order to talk about the official definition, so in order to write down the official definition, we need to discuss notation. All right. All right. So we will use, typically, we will use x to denote the input of a function. Okay. Okay. It doesn't mean anything yet, but just stick with me here. So we will use x to denote the input of a function. We will use f to denote the function. Oh, I completely messed this sentence up. We will use, let me say it like this. F of x, so this is read as f of x, f with parentheses right next to it with x inside. F of x is how you read this, to denote the function itself. So here's an example of a function. F of x equals x squared. Okay, so I'm saying that the function itself takes in an input x. So this little like parentheses x thing is like a little window into the function that says, you know, this is what's getting plugged into the function. This is the input of the function. And then what does the function do? So when the equal sign comes, that's saying, now here comes the rule for the function. And they can be very complicated, right? But here, what happens to this input? It gets squared, right? It gets squared. So what happens here, just with this little example, is we have this function f, or I'll say this function f of x, and I'll try to be particular about that. This function f of x takes in an input, takes in some input, which for now is just an arbitrary x, takes in some input x and squares it. Now, earlier I said that we're going to talk about different representations of functions, and this is going a little out of order because I'm only introducing this notation just so I can write down that official definition of a function, right? But since I've went ahead and given you a little quick example of what a function can look like, this is called the so-called algebraic notation. And I told you that this is going to be, or I'll say algebraic representation. That's what I'll say, algebraic representation. I told you that this would be one of the most, you know, the way we're going to look at functions the most, and you've probably seen something like this before. It's probably the most widely used, you know. No one's really going to just use like a verbal description of a function, you know, if they're trying to write it down. But just because I did write it down over here, this would be the so-called like verbal representation, like where you say or write down what the function actually does. This function f of x takes in some input x and squares it. That's all it does, right? It takes in some x and it squares it. All right. I don't want to do anything more with this example. This was just to talk about the notation, the f of x and the x. All right, so all of that was just so that I could write down this official definition of a function. So now here it comes. So a function f, the book just says f You could also say f of x, a function f of x, is a rule. Okay, so the rule part, that's just referring kind of vaguely to whatever's happening on the right side. Some rule, some set of operations, you know, squaring stuff, adding stuff, subtracting stuff, etc. Is a rule that assigns to each element x in a set A exactly one element called f of x in a set B. Okay, so that definition is coming straight from the text. Now, so let's talk about this. Okay. So what are they saying here with this set A and set B stuff? They're saying that this function, f of x, takes stuff from some set A. So this is like, A is like the set of inputs. So these are like the inputs, which is just arbitrarily, just like some random input, we're just calling the letter x. Just to be vague about it, just say it's just some x. Okay, and then there's another set that lives over here. They're both sets of numbers. That's all they are, is they're sets of numbers. Well, they don't have to be numbers, but for us, they're definitely just real numbers. So that's my set B of outputs. And what the function f does, so if I want to use the appropriate notation here, I guess I would say, you know, this f is if f is the rule, let's see what they did. That's why they didn't put f of x in their definition. Let's fix that. Let's just make this, let's just call it f. This is just getting it doesn't really matter. I just don't want to confuse you with the picture. So we're just saying f is like, the letter f is just representing sort of whatever the rule is, like squaring stuff or adding stuff or whatever. And the actual output that it gives over here will be denoted by f of x. So for instance, with that function that I gave earlier, let's say, you know, back to that example, f of x equals x squared. Squaring x is the rule that gets you from A to B. So let's let some number be in the set A, some number, say, it doesn't matter, x equals 2, be in A. Then the corresponding point f of x, which by the way, f of x is 2 here, so f of 2, you see I replaced the little input window with a 2 because I'm plugging in 2 into the function, equals 2 squared, which by the way is 4, whoops, is in B. So if I was to like draw my little picture, which I'll do this explicit example here in this picture. If I draw my little, I'll draw it all in green. So I'll just say like this is the green thing happening. Then the input element is 2. The thing mapping it across is that rule, that x squared thing, the x squared rule. So I'll just say x squared here. That's the rule that, oops, sorry, my phone just fell out of my pocket. The rule that gets us from input to output for this particular function is to square the input, and that's going to land us at a new element, which is just a number, f of 2, which is 4. So I'll just say f of 2 here, which by the way is 4. So you could just put 4 there. That would be okay. Okay, and x squared is a function because it doesn't do anything wild like give you two different outputs. It doesn't break the rules, right? Like giving you two different outputs for the same input. What it does do the thing though where there is another input value that can yield a 4. Does anyone know what is the other input that I can plug into this function? What other x value can I square that will yield a 4?
-2.
Yeah, good. -2. So let's just note, thank you. Note that f of x equals x squared does this, and I'll just say it does this, and then here's my picture. So it takes a 2 and a -2, and it maps to both of them to the number 4 over here in my from my inputs to my outputs. But that's okay. But this is okay. This is still a function. It's kind of a special function. I'm kind of making a big deal about this particular thing that's happening because later we're going to talk about a little bit more about functions that do this. But this is still a function. That's kind of why I'm making a big deal out of it now. Not all functions do this, right? A lot of them just take stuff from here to here, and there's no like overlap in the outputs like this. This is just a special kind of function. In particular, stuff that squares, takes in and squares things. Of course, it'll take positive and negative, square them, and end up at the same value. So just one example of a function that does this. All right. Now, since we're talking about these sets now, I've kind of moved into talking about these sets. Oh, by the way, before I go, hang on one second. I want to do one more problem that's explicit in the homework. Here's a homework problem dealing with definition of a function. Is it possible for f of 2 to equal 4 and f of 3 to equal 4? Okay. And then question 2, is it possible for f of 2 to equal 4 and f of 2 to equal 8? All right, let's take these one at a time here. You could even draw it, draw a little picture. So what's happening here, f of 2 equals 4, so I can just say like here's, I don't need like real big sets here. It's just a couple of elements in there. So I've got a 2 in here and a 3 in here. So that's my, I'm going to do it in a different color so you can see it. That's my 2 and that's my 3. Maybe I should have drawn it bigger just for your sake. But there's 2 dots in the first set, the set of inputs. The 2 dots are the 2 inputs inside the parentheses. That's where your inputs are, so a 2 and a 3. And they're both being mapped to 4, right? They're both being mapped to 4. So is that the situation that's okay, or is that... hang on. Oh, yeah, sorry, I just had it. Okay, is this okay or is this not okay? Well, we can look back at our, I drew some pictures at the beginning of what's okay and what's not. And I said that, I'm going to cover this up for a moment. It's okay for 2 different, so remember the function, it's in blue over here. It's okay for 2 different inputs to go to the same output. So this is, yes, it's possible. With the full question about these functions is it possible for f to be a function? So I'm shorthanding the question. You'll see it in the WebAssign homework later. So this is okay. Now this other one takes 2 inputs. Well, rather, actually, they're the same input, right? It's just the number 2. Oops, just the number 2 there. And it maps that 2 to a 4, 2 different outputs, Right, remember the outputs are on the right side of the equality, 4 and 8. Okay, but that's not okay. That's like the opposite case here. Right, you see the difference. Repeated, different inputs going to repeated output, that's okay. Repeated input going to different outputs, not okay. Maybe I'll write that down just to be, maybe that's I feel like I'm saying this whole function idea like over and over again, several different ways, but sometimes that's what it takes. And like one way of me saying it may not make sense to you at all. But then if I say it a different way, suddenly it makes a lot of sense. And then it's your job as the student to study and make those two ideas connect. Okay, so this one, I'll write down what I just said. Two different inputs. Going to same output. I'll just say check. That's function. Same, that's same input going to different outputs. No, not okay. All right, cool. I think I've said pretty much everything I can say about this without just starting to literally just repeat myself over and over again. I think I've kind of said it every single way I can think of, so I'm gonna leave the definition there and let's go on to talking about these sets that I introduced called A and B. Let's give them names and talk about let's talk about them. So the set of inputs allowed into a function is called the domain. The domain of the function, if I'm being absolutely complete in the way we talk about it. The set of inputs allowed into a function is called the domain of the function. Okay. So far, I've not shown you any functions that have any kind of domain problems. Like what, this probably doesn't mean much to you right now because you're like, well, I can't even like think of what does it mean inputs allowed into a function, right? So what I'm going to do to kind of explain this more is sort of give you anti-examples, like examples of things that do have values that are not allowed into the function. So let's consider the two classic examples here that we will talk about in this course. Consider f of x equals 1 over x and f of x, I'm gonna call it I'm gonna use a different letter here. G of x equals square root of x. So some common letter names we use for functions are f, g, and h. If I have to ever go beyond f, g, and h, I don't know, I'll just start using other letters. I might go back to the, A, B, C or something, but usually f, g, and h are like the classic go-tos. Okay. Okay, so these functions, so f of x has a particular value that is not allowed as an input. Namely, if you guys think about it, you think, okay, what cannot be plugged in for x here? Eventually, you'd remember, oh, we can't divide by 0, right? So x cannot be 0. So when I say that domain is the set of inputs allowed into a function, why do we even mention this domain thing? Like, why would there ever be stuff you can't plug in? Well, this is one particular case where you do have a restricted domain. So a lot of the functions we're going to look at will have completely unrestricted domains, meaning you can plug whatever the heck you want into it as long as it's a real number. But these two functions, and I haven't talked about this one yet, but so this function has a restricted domain, namely that x cannot be 0, one particular number. Okay. How do we denote this? How do we write down then? How do we write it down? Because I can say it in words. I can say f of or I'll say the domain of f of x is any real number except for 0. Right, I could say that in words, I could write that sentence down, but how do we write it, this f of x? No, let me say, how do we write the domain of f of x? Oh, down mathematically. In other words, I want to take the statement, of, what do I want to take the statement of? I want to take the statement, the domain of f of x is all real numbers except for x equals 0. Or I could say, except that x cannot be 0. That's just depending on the grammar of your sentence, whether you'll say, equal 0 or not equal 0. It just depends on how you set it up. You could say all real numbers, but x cannot be 0. Just the way I grammatically set it up, I'm going to say all real numbers except for x equals 0. Now, how do I translate that into a mathematical statement? Instead of a sentence like this, I need like a... So the first thing I'm going to do is domain, capital D for domain with a colon. So this is domain. And then I'm going to use interval notation. Okay, so we're probably going to have to go on a tangent about interval notation, and we will, but I want to get it down for f of x, and I want to get the domain down for square root of x, and then we'll go back and go on a little tangent about interval notation. So how would I notate this? Well, all real numbers would be negative infinity all the way up to positive infinity. So I've got the bottom half of the real numbers, no problem. I can plug in like any negative value, right? It doesn't matter. It could be negative 5 million. It could be negative 1 over 74. It doesn't matter. But I cannot plug in 0. Right, so I can get right up to 0, but not including it. So remember, a parentheses there, a parentheses symbol means I'm not including. I'm getting right up to 0, like negative 0.000001, super close to 0 from the negative side, but not touching it. And then right after that, I'll leave a little space here, I pick back up and go off to positive infinity, because I can also plug in whatever the heck I want in the positives, as long as it's not 0. So on this side, I also get right up on 0 without including it. And I denote not including it with a parentheses symbol. So I could plug in 0.00001, right? But as long as I never actually plug in 0. So I'm getting as infinitely close to 0, as possible, but not including it. And how do I stick these two sets together? I use this symbol called a union, which if you've probably none of you have taken finite math, MS 110, but if you have, then you're kind of at an advantage here because you've seen that symbol before. That's called a union symbol. So like I said, I'm going to go in more detail about this, but first let me get the, or you know what? No, I changed my mind. I am going to go into detail about this, and then we'll come back to talking about g of x. And then that'll probably take up the rest of class today. Okay. All right. So how is this working? So like what, how did we get here? How did we get from this statement to this thing here? Okay. The domain of f of x is all real numbers except for x equals 0. Can we draw a picture of that on a number line? Yes, we can say, here's all the real numbers. Here's 0. So over here is negative infinity and positive infinity. How do we draw this thing? How do we say, I want to, so in red here, I'm going to draw all the things that are allowed in my function f of x. But every single number down here is allowed, all these, all the way right up to 0, and I'll put a hole there at 0. So that's like a dot, like an open dot, like a hole punched out at 0. So don't be confused. That's an open dot, and that's the number 0 there. And then it picks right back up over there. Right back over there. That's a picture of our domain of f of x here. Now, when our domain is split into two pieces, like this, into two pieces, we will have two separate intervals. Okay, what are our two separate intervals here? Well, this one on the left here, actually here I'll say, I'll just number, just for reference, I'll call this 1 and this 2. So the left one, the one that I've notated as number 1 here, you always read them from left to right. So on the left is my negative infinity, and you always put parenthesis symbols around the infinities, whether it's positive or negative. And then it ends, this interval ends at that hole on the number line. And what number is it ending at? That 0. And we use parentheses. The parentheses mean we are not including 0. If we used a bracket, like a square bracket, that would mean we are including 0. But we specifically want to not include 0 here, right? And technically you never include either of the infinities. Don't worry about that. Just remember that you always wrap the infinities with parentheses. Okay, now the second half, again, reading from left to right, I'm starting at part 2 here, reading left to right. The leftmost part is that 0, but again, not including it. So parentheses again. And the furthest number, of course, is going to be that infinity wrapped in parentheses. Now, shoot, I'm out of room. Okay. Now, we need the union symbol, capital U looking thing. It's not a capital U, it just kind of looks like it. So don't put a tail on it because it's not a capital U. The union symbol to sort of add, to stick our intervals together, to add our intervals together. That's how we end up with, hang on, this. Okay. All right, so now I want to talk about g of x. First, last thing about f of x here, I want to give you a problem to try. And then we'll talk about g of x, and then we'll end. Find the domain of f of x equals 1 over x minus 1. And I'll give you a hint, it's going to look very similar
It's just going to be about finding that number that x cannot be. So it's going to be negative infinity up to some number, union with some number again. So you got to figure out what goes here, and here. X cannot be, I'll say this. This should be the number that x is not allowed to be. So maybe you've already figured it out, but just it's a little quick homework problem for you to try. Okay, let's talk about g of x. I guess I can work off of this paper. So g of x was equal to, just to remind you, is square root of x. This also has restricted domain, but not the same way that f of x with the 1 over x did. Not the same way that these 1 over x things are going to act. G of x does not have a particular value that cannot be plugged in. It has many values that cannot be plugged in for x. Many values that cannot be plugged in. For f of x, it was can't divide by 0, right? So that was just one particular number. Now here, g of x has many values that cannot be plugged in for x. Namely, you cannot have negatives under a square root. X cannot be negative. So how do I denote that? So the domain of g of x is all real numbers except for negative values. So if I drew that as a picture, negative infinity up to positive infinity. 0 is going to matter again here because why is 0 mattering again? Well, because that's where numbers switch from positive to negative, right? So if I drew a picture of my domain, I want to be able to include 0, so a closed dot at 0. I'm including 0 because 0 is allowed. Square root of 0 is 0. That's fine. I just can't plug in negatives. So do I want to go this way or this way? Well, of course, I want to go to the right, right? I want to get all those positive values. So how do I notate that? Domain, colon, bracket around 0 this time because I am including 0, off to infinity. And that's it. For square root stuff, the domain looks much simpler because our interval is not broken into two pieces. Back here, when you've got a division by x, like in f of x, your domain has to be broken into two pieces. That's why it looks worse with the interval symbol and the union symbol and all that. You don't need that for a square root of x thing because we're not just punching a hole in the number line. We're like getting rid of half of it, right? We're getting rid of a whole chunk of it. Okay, so the domain should look easier here. Now, here's another little practice problem to try. Find the domain of a similar function, g of x equals square root of x minus 1. And I'll give you a hint, it's going to look very similar. Again, it's going to look very similar. There's going to be a bracket and then off to infinity, but you got to figure out what is the cutoff number here. It's not 0 anymore, because if I plug 0 into this function, I get a square root of -1, which is not allowed for real valued functions. So what number must it be to balance out this x minus 1? So we'll talk about that. Now let me see, oh, of course, WebAssign logged me out. Before we go, because we still got 10 minutes, so I want to look at the homework and see if I'm leaving anything out that I should be telling you about these earlier parts of 2.1. Come on, there we go, 2.1. Expand all. We still need to talk about evaluating functions, but that'll be easier, probably. Okay. Yeah, evaluating functions. All right, last thing here, last thing, and I promise I'll let you go. This is a homework problem from Hawks that I just want to point out because, or not Hawks, WebAssign, sorry, I'm thinking about a different class from WebAssign. Which of the functions have 8, the number 8 in their domains? And then they give you these 3 functions. A is f of x equals x squared minus 3x. B is g of x. Oh God, sorry. Trying to go too fast, I'm messing up. G of x equals x minus 8 over x. C is h of x equals square root of x minus 16. Now, no reason to think that 8 is not allowed in this function, right? Because the only time we're going to have restricted domains is when you've got square roots and division by x. So we should be suspicious of these two, but this one's totally fine. You can plug 8 into, you can plug whatever you want into this function. So this one, 8 is in that domain. Now here, what do we get when we plug 8 in? G of 8 is equal to 0 over 8, but that's just 0. That's okay. You can have a 0 on top. 0 in the bottom is bad, but so this is okay. This is okay. What about h of 8? That gives me square root of 8 minus 16. That's not okay, because that's going to be a negative under there. Okay. Just wanted to point that one out. Sometimes they ask questions that are a little different than what I did in lecture. So, all right, you guys are good to go. Stick around if you have questions. We'll finish 2.1 and probably start 2.2 on Monday.